Okay. We can get started at number 3.
Okay. So, so the B is going into the board. So this is going straight into the B's to the board. So you want your electric field to come to the left, going to the left. No. Wait. I fixed it. So the force that the B is going to cause is going to go to the left. So this is going to tend to swerve to the left. So then I want an electric field that's going to go to the right. So then to make an electric field go to the right, I just put in an electric field to the right because it's a proton.
You got your answer?
Which,
All right, let's see. So, first of all, you had to figure out the effect of the magnetic field. So it looks like you got that right. Now, it would be a good thing, I don't know if you did that, to write down what the direction of QV is. So what's the direction of QV here? Because we're dealing with a proton, and V is up. So our fingers are pointing up, our palm is into the page, because that's B, and then you're right, your thumb is pointing to the left. So FB is to the left, and then you figured out that you wanted FE to the right to balance out FB, that's to the left.
and since it's a proton, you just put the electric field in that direction.
For a positive charge, the electric field and the electric force should point in the same direction. So what was the answer to A?
So your direction is to the right.
Good. Now in this case, we have to say, is that X, Y, or Z direction?
X.
Positive X or negative X? So you're not going to get full credit on this one since they gave you these axes. You'd have to say the direction of E is the positive X direction. So you should always watch out when the problem is giving you axes, but that was a good way to work that out. Okay.
And then magnitude will be the same type of thing. So you want.
Right.
So the magnitude of FB here is QVB. QVB to equal QE. So E is V times B.
Now the charges are the same again. This is the same answer we got before.
Yeah.
It's just in the previous problem we were solving for B, and here we're solving for E. In the first problem I gave you, you were given an electric field and you got to choose the magnetic field. And in this problem, we're given the magnetic field and we get to choose the electric field, but it's the same answer either way. So what was the magnitude? V times B, and the direction was the positive X direction.
Yeah.
Okay, so this is really pretty much the same as the problem that we did before. Good.
With these same E and B fields, select the same velocity if the electrons were, or if the particles were electrons. It'd be like they have to be inverse, or like opposite. Well, if it was electron, then the force, the magnetic force would be to the right. So then you would need to put your electric field, you want your force of the electric field to be to the left, but then to get that, you would still put your electric field to the right, so it'd be the same.
The same?
Yeah.
That's interesting. So now QV is down. So now if the magnetic force on the proton was to the left, the magnetic force on an electron would have been to the right. So that's changed. So now we want the direction of the electric force to be in this direction.
But the electric field is still there.
But the electric field should still point in this direction. That's right, because for a negative test charge, the force in the field point in opposite directions. That's interesting. I was guessing at the beginning it wouldn't be the same. So do we want the same direction electric field as before?
Yeah.
Yeah. And how about the same, do we want the same magnitude?
Yeah.
Yes, because B hasn't, because the properties of the electron don't really appear here. B hasn't changed, and the V we want hasn't changed. By the way, I guess I shouldn't be calling this B. I shouldn't be calling this V. We have to use the same symbols as in the problem, so we should be calling this VY, since that's the symbol they used. So the answer was yes?
Yeah.
Yeah, that's interesting. Okay, good.
Okay. Would the same E and B fields select the same velocity if they were neutrons? If they were neutrons, would it even do anything?
You tell me.
It wouldn't even matter. Like, they just still go straight through. They
Okay.
wouldn't even be affected by the fields.
So what's your answer?
Yes.
Yes? Now remember, here's the whole point.
Well, it doesn't matter. Doesn't it not
Let's
matter?
say that V sub y here is, I don't know, 5 meters per second. The whole point of this apparatus is if you only want particles that are going at 5 meters per second to get through. So for example, if V here is 5 meters per second.
Well, it wouldn't select the same velocity. It wouldn't. It would just send it, everything would just go through.
Exactly. So for neutrons, there would be no selection. For neutrons, any velocity is going to go straight through. For protons and electrons, some velocities are going to go straight through, some velocities are going to curve to the right, and some velocities are going to curve to the left.
Yeah.
But for a neutron, all velocities are going to go straight through.
Yeah.
By the way, so let's say, yeah. Let's stick with the electrons here that have the force to the right. Let's say that the velocity is too big. If the velocity is too big, is the electron going to curve to the right or curve to the left?
Oh, it'll. Oh, the velocity.
Let's say that the
only
electron
matters
is going
for
really,
the
really
electric-
fast.
For the magnetic field, so it would go to the right.
That's right. If this velocity is really big, then the magnetic force will overwhelm the electric force. But we saw that for the electron, the magnetic force was to the right.
Yeah.
So if the electron is going too fast, the magnetic force will be too big and it will curve to the right. If the electron is going too slow, the magnetic force will be too small and it will curve to the left. And only when the electron is going at exactly the right speed, E over B, is it going to go straight through. This is how this is a device that selects only for electrons at certain speeds. However, if a neutron is going really fast, it's going to go straight. And if a neutron is going really, really slow, it's still going to go straight. All the neutrons are going to go through, so this is not a device that you can use to select certain speeds for an uncharged particle. Now, this is something that could be used in real life again. Suppose that you're trying to make a particle accelerator, and you only want to let particles going at a certain speed through. This is a good device to make sure that you know at the exact speed that the particles are that are going through, but it only works for charged particles. All right, well, this is a really classic type of problem on these types of tests, where you have to combine the electric and magnetic fields. One thing is, this might have been easier for us earlier in the course before we learned about electromagnetic induction, because I was confusing our thoughts here. These B and E fields are not inducing each other. That only occurs when the B and E fields are changing. Here we have constant B and E fields, so this has nothing to do with induction. And actually, I think once we saw that, I think you remembered a lot of important stuff. You remembered the right-hand rule. You saw that we had to set the forces equal to each other. I think you remembered these formulas, so you remembered a lot of the stuff that we talked about earlier for how to apply that. Sounds good? These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you.